So what you guys are going to do this week is synthesize some aspirin. It does kind of have an interesting past, and depending on who you talk to, I think it gets more interesting. Aspirin is originally derived from salicylic acid, which is a natural product found in willow bark. So as a natural remedy for aches, pains, fevers, that kind of general thing, people would chew on willow bark, and that would release salicylic acid into the bloodstream, go through your digestive system, all that fun stuff. You could cure your headache, you could break fevers, that kind of fun stuff. If you're well, let's go with the optimist view first. The optimist view is that somebody was having or prescribing willow bark to their patient, and their patient kept getting upset stomach, complained of the side effects of this compound. You've got two very acidic groups on salicylic acid, so you could potentially see some reasons for why there'd be secondary side effects, like upset stomach. And so they said there's got to be a way we can change the structure to mitigate some of that side effect, and what they ended up doing was adding what's referred to as an acetyl group. Now, that group on the end is an acetyl. And by doing so, they got rid of a lot of those side effects. You don't get quite as upset stomach, that kind of fun thing. Okay, so that's looking at the world as all bright and fluffy and happy. If you're an angry person like me, I guess, instead, I would make the argument that they didn't really do it for those strict methods. Does anybody know how many patents there are of natural products? Zero. Why are there zero? You can't patent natural products. How many patents are there for aspirin? They've got a pretty big patent on aspirin. Bayer was one of the first people that patented it. They've got a huge revenue source from aspirin. It's still the same drug. It's still doing the same thing. They just reduce some of the side effects. The active ingredient is still salicylic acid, but because they minimize some of those side effects, hey, they can patent it, and now they can make millions of dollars, and nobody goes to the natural source anymore. Okay? So yeah, if you're a pessimist like me, they did it so they could make money. If you're an optimist, they did it because they didn't like people being upset stomach. Okay? So just kind of an interesting piece of, I guess, somewhat history about it. As far as the experiment goes, it's a fairly straightforward experiment. It's very commonly done for first semester organic students because it goes so well. Okay? So you'll take some salicylic acid, you'll mix that with acetic anhydride and some phosphoric acid, and then you'll heat that very, very mildly, which is why we're going to end up using a water bath to heat this, as opposed to heating it on a hot plate. Okay? Most hot plate syntheses will heat it up too much, and you end up pushing a whole bunch of side reactions, so it has to be done in a water bath. At the end of that time, roughly 15 minutes, really not very long, you can turn off the heat, but you'll then want to add water. Water is being added to neutralize the reactivity of some of the other reagents. Acetic anhydride is a fairly reactive species. Phosphoric acid is also fairly reactive. So we add water to dilute as well as neutralize the acetic anhydride. Okay? That reaction does require a little bit of heat, which is why we turn off the heat, but we still leave it warm. We don't wait for it to cool down, okay? Because that helps speed that reaction along, and we can get those reagents neutralized fairly fast. Okay? We're also going to do it through the air condenser and not just in the conical vial. While that reaction is fairly slow at cooler temperatures, it is still an exothermic reaction. And if you add it to just the conical vial, it'll probably end up boiling instantly and spitting your product all over the place. If you do it in with the air condenser attached, it'll spit and boil, but it won't leave the flask. Okay? It'll get trapped by the air condenser. At that point, you can cool everything down. You should see crystals, so you can go ahead and filter those crystals out. You'll collect those via Hirsch funnel filtration. You should end up with your final white product. You can get a melting point and perform a classification test. Okay? So everything is fairly straightforward. Really the only new thing would be this classification test. Okay? And what we're going to end up testing for is the functional group of a phenol. Okay, so you'll take a small amount of your compound, or any compound, dissolve it in roughly a milliliter of methanol, and you'll add a few drops of ferric chloride. At that point, you just observe it and see what changes. Okay? Very similar to what you did with the bromine test. You added bromine, see what changes. Okay? In the presence of a phenol, ferric chloride undergoes kind of a mild substitution reaction, and you'll notice the chlorides leave, and what we end up switching out with is this big complex. Okay? The interesting thing about that complex is we got a lot of double bonds, a lot of electron density. All of that electron density is conjugated. All those double bonds can pass electrons between one ring to the next. Okay? Most colors that we see in everyday life as dyes for our clothes are due to organic compounds, and it's the conjugation of the pi systems that allows for different colors. So when we run the ferric chloride test, a phenol will start to conjugate with the iron compound. Because we've got all that conjugation, we see brightly colored solutions. Okay? So what you're going to end up looking for is that nice bright color. Okay? How is this going to be particularly helpful for us? Okay? If we take a small amount of our starting compound, okay, do we expect to see a result? Or sorry, our product. Let's take a look at aspirin as a product. See lots of oxygens, see a decent amount of double bonds. Would I expect to see a result? Remember, your classification tests for a phenol. The phenol is the alcohol attached to a benzene ring. Do we have an alcohol, an OH, attached to the benzene ring in your product? Not directly. Okay? If we don't have that alcohol directly attached to the aromatic ring, we don't have a phenol. If we don't have a phenol, can it coordinate with the iron trichloride? No. Which means, what's our end result? No conjugation, which means no color change. Okay? Well, that's kind of a useless test then. Okay, so what else could we do? In theory, as we did this reaction, we converted salicylic acid to aspirin. So what we can also do is test for our starting material and see how that responds in the presence of ferric chloride. Okay? Does our starting material have a phenol? Yeah. We've got the phenol right there. Okay? So our starting material will coordinate with ferric chloride, and we would expect to see a conjugated system, so a lot of color. In the case of your product, we would expect no phenol, which means no conjugated system, which would also hopefully imply no color change. Okay? So that's going to be part of the experiment for you to decide and see what's happening with that. Questions about any of that? Okay. We haven't spent a whole lot of time looking at this kind of analysis, so I'm not going to spend a whole lot of time now because it's not going to add anything at the end of the semester. But when you look at an individual reaction, you should be evaluating your starting materials and your products, or your ending materials, and try and see what things have changed, what things have appeared. Okay? So if we look at our starting materials, we would expect to put in our reagents, any catalysts if we wanted a catalyst, and solvents. Okay? If we go to our ending material, okay, what things would we expect to see at the end of a reaction? There you've got your product. Why might you see catalysts at the end of a reaction?
Catalysts appear in both.
Yep. Catalysts are not consumed, are destroyed, or created, which means if we start with a catalyst, we expect to see it at the end as well. You might also see byproducts or side products. Okay? Byproducts would be something that's a natural occurrence from this reaction. So in this case, we form aspirin as our desired product, but we also form this molecule. Okay? A necessary repercussion of this reaction. That molecule ends up being called a byproduct because it's forced to form in the process of the reaction occurring as it goes. Okay? Side products would be other reactions. Okay? With most reactions, as we're about to look at, there's lots of positives and negatives. Those positive atoms and negative atoms can combine in varying ratios and amounts, causing different things to occur. Okay? Those ultimately end up being side products, and those will do what to your percent yield? Any guesses? If you form a bunch of side products using the same materials that you use to make your final product, what would happen to your percent yield? Does what? It should decrease, because you're taking your starting materials and instead of turning it into your product, you're turning it into other things that you aren't going to isolate. So you would expect your yield to go down. Okay? In most cases, we try to limit and choose the reagents very carefully so that we minimize the formation of side products. So this is where it's going to get a little bit more dicey, and you guys are going to see this in the group activity. Okay? We're not going to show you directly the mechanism in recitation. We're going to make you kind of work through it in the group activity. So as we've done with previous labs, what you need to go through and do is identify bonds broken and bonds formed, identify sources of reactivity, positives and negatives, and then hopefully also start to look for patterns and ignore parts that don't change. Okay? If it doesn't change, we don't need to worry about it. We don't have to be concerned about that jumping in, changing our bond structure. Okay? If you become more advanced, instead of looking just for positives and negatives, you can classify them as Bronsted-Lowry acids and bases, Lewis acids and bases, nucleophiles, electrophiles. Okay? That kind of next level tier. The pre-lab is going to have you go through and identify wherever you have a positive atom and a negative atom, and trying to match those up and see what's happening with it. Okay? So the group activity should get you on a first start so that you know which ones are actually going to react. Your pre-lab's getting you to look and recognize all of those pieces. Before we let you run completely into it, okay, I do want to take a closer look at our reaction. So we want to go through and identify what I've just asked for. Okay? Identify our bonds broken, bonds formed, positives and negatives, all that kind of fun stuff. So how about bonds broken? I hear an OH. What OH? Where? Here? That was an OH. What are you saying? This one? Here, let's try it this way. Oh, now I got you.
Yeah. If you get this wrong,
See,
it didn't mark.
It's not that easy, is it?
Doesn't mark. Yeah, you said. How does it mark?
Oh, that's my fault. I changed it to the eraser. So there's an easy bond to break. Where else? What other bonds broke? This time not OH. We've got a bond in there. Bonds forming. Okay. Does everyone find those obvious? I don't personally find them obvious, so if you find them obvious, good for you. Okay? It's not the easiest thing to recognize exactly where everything broke. Okay? You might go through and start to suggest other places where things shifted around. That's okay. As far as predicting this actual reaction, shifting to reactants and products, the idea is to try and find it as best you can and see what you can come up with. As far as positives and negatives go, that would be the next part on trying to figure out what's happening in this. Okay, let's go ahead and start with blue. This hydrogen, what charge might you expect that hydrogen to be? Positive. Why should that be partially positive? It's attached to an electronegative oxygen, which means the oxygen should be. If we go through and address the rest of that structure, the other oxygens will probably be negative as well. That hydrogen will probably be positive. Okay, so we've got a couple positives on hydrogen, so let's kind of ignore those for the moment. Well, let's not ignore them. Let's take a look at our oxygens. Which of those oxygens would we predict to be the most negative? It's a harder thing to ask. Probably a first good guess to go with is where our bond initially broke, where we actually had some chemistry occurring, because very clearly that was positive or negative enough that something happened in that area, which would suggest that that oxygen atom is probably the most negative. How else could we do that? You could go through and evaluate resonance options on every single atom, and you'd end up finding that that oxygen has the least valuable resonance options. Okay, what does that mean towards its reactivity? If it has the lowest amount of resonance, it has the highest amount of reactivity. So if we have a partial negative, what do we need to find in our other starting material? Something positive. Where's the most positive atom in that middle compound? This one's a little bit easier to work with, in my opinion. Carbon, good call. Which carbon? Should I try this again? The one with the double bond. Oxygen, why? Look at what's attached to it. It has two very electronegative elements attached to it, meaning a lot of that electron density is getting pulled away by those electronegative oxygens, making that carbon very positive. Is there another positive carbon in this structure? Not on the other side. Is there a difference between those two? No. Which is one of the things that we add into this reaction. We want to control that and make sure that we only have one type of positive atom. If for some reason we added two, what does that mean? We get multiple products. We end up with a lower yield of what we would want. Okay? So the next thing that we'll try and do is go through and ignore the sections that didn't do anything. We said this oxygen, said this oxygen was our most negative, this carbon was our most positive. Did anything happen to this structure out here as we went from reactant to product? No. So instead of looking at that as a giant big group like that, maybe we should just write this as ROH. And what we end up with as a product is RO. And what changed about that oxygen? It's now bound to that carbonyl, or our acetyl group. What's our other starting material? Where now this could be R prime and R double prime as a new possible species, which means our product R prime or R double prime. Okay? Whatever those R groups were irrelevant to our reaction. We're only concerned about what's actually happening where the chemistry is exchanging places. Okay? This part of it that we just walked through is the hardest question on the group activity. Robin, you can go ahead and pass that out. Okay? Which is the very last question. Okay? Everything else is easier, but that doesn't make it easy. Okay? What you're going to be evaluating is individual reactions.